So I gave you a homework problem in the last class. How many of you could solve the problem? So I gave you this problem. So did you try this problem at least? Did anyone try this problem? So no one tried this problem? Okay, let us try this problem now. So there are two events there. And the problem setting is you have 10 coins. 9 of them are fair. 1 is bad. So out of 10, 1 is bad. And how it is bad? If we toss it, it always shows the tail. Now we picked up a coin at random and tossed it, and we found that we tossed it 4 times. Every time, tail came up. Now we want to know if we pick the bad coin. So we want to know probability of A, given that we found 4 tails after we picked up the coin. Now what is the probability of this? So what do you think the probability will be? So if I say it's just 1/10, how many of you agree with me? Do you agree that it's 1/10? Who do you think that it's not 1/10? I'm wrong. Who thinks that? So did you even understand the problem?
Yes, sir.
All right, so now let's solve the problem. It's not actually 1/10. So we need to find out probability of A given B. And we want to find out if bad coin was chosen, given that we found 4 tails in a row after we tossed the coin 4 times. There are 4 consecutive tails. So from this statement, we can think that it is highly probable that we picked the bad coins. we pick the bad coin. But still, we want to know the probability that we picked the bad coin. Now, we can use Bayes formula for that, for solving this. So, given we pick the bad coin, given that there are 4 tails, it is harder to solve. On the other hand, if we reverse the problem, that what is the probability of tail given that we pick the bad coin? So it's easy. It's already stated in the problem. So we can reverse it. And when we, if we think, Bayes formula gives us opportunity to reverse the problem. So whenever we see that if we cannot solve it because the conditioning is too hard, and if we reverse the conditioning, then it becomes easy. Then we can use the Bayes formula. So here we'll do the same. So probability of A given B, it should be probability of B given A into probability of A divided by probability of B. Now here, probability of B given A, that means probability of all tails given bad coin is chosen equals what? Can you tell me what will be the probability for probability of B given A? Read the problem and you will understand. I'll wait for your answer. Read the question. So can you tell me the probability value? So the probability value of this term, probability of B given A, will be 1. So how it is 1? Here we see that if we choose the bad coin, then always comes up tails. That means if we already choose the bad coin, then it will always show the tail. So the probability is 1. So for this term, probability is 1. Now we need to find out probability of A divided by probability of B. Now here,
Hello, sir.
yes.
Sir, maybe someone trying to attend to the class. So please admit. মানে একজন ট্রাই করছে আর কি ক্লাসে অ্যাটেন্ড করতে।
So I need to find out probability of A divided by probability of B. Now probability of A here equals probability of the bad coin is chosen. It should be 1 by 10. Now probability of B all 4 are tails. Basically, we can find all 4 are tails in 2 different ways. Probability of all 4 tails given bad coin, and then probability of all 4 tails given good coin. So now all 4 of tails given bad coin 1 by 10, because it's just the probability of all the bad coin is chosen. Now probability of good coin, it is 9 by 10, and then all 4 are tails for a good coin should be 1 by 2 into 2 into 2 into 2 equals 1 by 10 plus 9 by 160. Now if you calculate, you'll find that its value should be close to 0.64. Its value should be 0.15625. Now if you plug in these two values, probability of A given B should be 0.1 divided by 0.15625 equals 0.64. So we see that even if we found 4 tails, 4 consecutive tails, we still have probability of only 0.64 that we picked the bad coin. Is it clear?
স্যার কোশ্চেনে কি এটাই জানতে চাওয়া হয়েছিল?
Read the question, then you'll understand.
কোশ্চেন স্যার মানে ইভেন্ট এ আর ইভেন্ট বি এর কথা বলছো, মানে কি জানতে চাইছে ওটা এখন বুঝলাম না।
কোশ্চেনটা ছিল হচ্ছে যে আমরা 4টা একটা কয়েন পিক করলাম, পিক করার পর 4বার টস করলাম, প্রত্যেকবার টেল আসলো। So the question was, what is the probability that we picked the bad coin? So is it clear? If it's not clear, you can ask questions. Okay, I hope all of you understood the problem. Now we'll do-
Sir, could you go back to the question slide for one moment? Sir, here it says the bat coin is chosen. So we are not choosing a coin every time we toss, right? We are choosing one coin and then tossing it 4 times,
yes,
right? So we are basically choosing one coin and then we are tossing it 4 times instead of choosing a coin every time we choose to toss,
yes,
right?
yes.
Okay, sir. Yes. So it's clear now. Yes, sir.
Any more questions? Okay, now let's continue with the slide. So today we'll start from independent random variable. Independent random variables are random variables for which this equation is true. So the joint probability distribution, the probability of a joint event, the value of this will be same as the separate event values, probability of separate event values. For example, if we think of a standard deck of card, then we can understand it better. There are 4 suits and 13 numbers for a standard deck. Suppose we want to find out the probability of 7 of hearts. Now, if we want to find it out, then if these 2 random variables, x and y, x representing the suit, y representing the numbers, if they are independent, then we'll find something like this. Probability of x, y of a joint event should be equal to probability of x times probability of y. Here, probability of 7 of hearts, there are 52 cards in a standard deck, and this is just one of them. And only one card has this tag. So the probability of this should be 1 by 52. Now, probability of x, that means probability of heart. Y means probability of 7. Y is the number, so we should write there y and x. Now, probability of heart, there are 13 cards out of 52 for hearts, so it should have probability of 1 by 4, and there are 13 different numbers, so the probability will be 1 by 13. Now, if we multiply these two, we get 1 by 52. So we see that probability of 7 of hearts equals probability of 7 times probability of 1. So here for standard deck of cards, picking a suit and a number, and if we assign these 2 events to 2 random variables, they will be independent random variables. We can check with a joint probability distribution too. For example, we have 2 random variables here, x and y. X can take one of these 3 values, y can take one of these 3 values, and this is the joint probability distribution. Now, we want to know if x and y are independent or not. So we can say that they are independent if we can find something like this. Now, I'll take a few minutes. Oh, sorry. Yeah, recording was not on for some time. So if do you have any questions? I'm giving you some time to think what we're doing here. Suppose we have a data set of images containing cats and dogs only. So if we form probability distribution, from which features do you think will form probability distribution? Can you tell me what, based on what random variable will form the probability distributions? If we have a data set containing only images of cats and dogs. So if we have a data set of cats and dogs, how many probability distributions do you need to for building a classification model? It will depend on the number of classes. So we'll build distributions for every single class. So we'll build distributions equals to the number of classes we have. Here we have 3 different binaries. That means 3 different classes. And for each class, we are building one probability distribution. Here we discussed how can we find the prior. Prior means even before we have anything, the features or anything. Can we say the probability of a data point? We can say probability of a data point based on our data set. So we take statistics from the data set, and from them we can say the probability of a class, and that's basically our prior. Normally for modeling the probability distribution, we use univariate Gaussian distribution or normal distribution. So this is our distribution. So here we're using the random variable x. This is for only one feature because it's one-dimensional distribution. Here we are using the features in x-axis, and we are getting the probability value in y-axis. Now, the equation is like that. This is a constant term, and this is the variable here. So the most probability is around the mean. This is the mean, around the mean of the distribution. And as we go left or right from the mean, the probability value exponentially drops off. Normally we use this because we can start from here, and after the training process, we can convert it to many other distributions. This is the most flexible distribution to start with. Maybe our data set has different distribution, but if we start from normal distribution, we can find the actual distribution of our data set. But this is kind of initializing our distribution. And then from there, after the training process, we'll find the actual distribution. So this is a real plot from the 1A data set. This is the plot for one feature, alcohol. Now, we can say that it is not really normal. We are just making up that it's normal. Normal is this feature is normally distributed. Actually, it is not. Yeah, it's true. Actually, it is hard to say that it is normally distributed. But here we have only data set for 130 bottles. And still, there are some patterns that it may be normally distributed. So for this small data set, we are certainly not sure that it is normally distributed. We get some hints, but most often we'll have a larger data set than this, and then we'll see that most of the features are really normally distributed. Or if it's not, then even we can change the distribution, and we'll discuss about it in our next classes. Now, this is the distribution of all binaries in this example data set. So here we said that we see that this is the distribution for class level 2. This is the distribution for class level 3, and this is the distribution for class level 1. Now, using just one feature among these 130 bottles, if we try to classify, we'll see that we incur 29% error, or we get accuracy of around 71%. Given that we have only one data set containing 130 rows, the result is not really bad. And we used only one feature. Actually, we have 12 more features. So hopefully, if we use more feature, accuracy will improve, first thing. And we can also discuss how we can classify a new point. For example, if we have a new point here, means we just got a new data set, a new row for a bottle. And in this new row, the alcohol content is maybe 13.6. So we use 13.6 in this feature space and try to classify the new bottle. Now, for 0.6, the probability for that it came from binary 2 is this, just this. The probability that it came from binary 3 is this. The probability that it came from binary 1 is this. Now we use this probability value and the prior value. So for binary 1 should be prior of binary 1 times this value. Suppose some value. For binary 2, prior is 0.39, and when probability value just this is much smaller value than the earlier one. And probability of binary 3, 0.28 times this value, and whatever value comes as the largest, we'll take that and we'll classify the new point to that tag. So this is the end of probability lecture. If you have any questions, you can ask now. Any questions? If you don't have any questions, we'll start our discussion of the next topic. So this is our next topic. So today we'll discuss some basic linear algebra so that we can interpret the machine learning models, or what we really do to understand that.
So sir, we static slide টা থেকে কি কোশ্চেন, কেমন কোশ্চেন আসতে পারে, আপনি কিভাবে কোশ্চেন করবেন?
Normally, I can give some problems that you need to solve using base formula and some prior and some basic probability things like what is joint probability distribution, what is marginal probability distribution. So how can we find marginal distribution from joint distribution, something like that. If two random events are independent or dependent. So basic calculations. If you just know the formula, you'll be able to do that. You'll be able to solve those problems. Now you may think that I really do not need to know these things, but if we really want to interpret the machine learning models, or if you suddenly stuck into a tricky problem, you will see that those insights will help you a lot. Any more questions?
So thank you.
Okay, so if you don't have any questions, you can continue our discussion now. So the first thing we will discuss, what do we mean by data in machine learning? So whenever we say data, we draw a diagram like this. We draw a diagram like this. Now, why do we draw a diagram like this? Basically, to represent our data, we use a high dimensional space. For example, if we have a two-dimensional space only, and we want to represent these data, we can represent them like this. This is feature 1, this is feature 2, feature 2, this is feature 1. Now we'll have a cell for feature 1, we'll have a cell for feature 2, and then we'll represent each data point as a row in this data set. For example, we can put it here, next one here, this one here, and this one here. Now for this data point, the value of feature 1 is 3, value of feature 2 is 5. So 3, 5. Now we don't have a tag here, but maybe we'll have tags like A, B, B. Then we will have a tag like tag here, A. For the next data point, also tag is A. Feature 1 value is 2, feature 2 value is 4. For the third data point, feature 1 value is 1, feature 2 value is 1, tag is B. For the fourth data point, feature 1 value is 5, feature 1 value is 2, feature 2 value is 5, and it is tagged as B. So we represent this data like this. Now for our convenience in calculation, we also represent this data set like this: 3, 5, 2, 4, 1, 1, 2, 5 as a matrix. So when we represent this as a matrix, then it becomes easier to calculate. We can also represent it like this. So we can represent this any way we like. Any questions? So we use vector and matrix a lot in machine learning. Normally, to represent a vector, we use notation like this. We write the numbers in a column, and for matrix, we use a formation like this. Here, each entry Mij, the first index normally indicates the row ID, and the second index indicates the column ID.
Sir, so sir, আপনি যে বলেছিলেন যে what do you mean by data in machine learning? So এর আগে previous slide যে দেখালেন, তো মানে এটা কি অ্যানসারটা কি হবে?
So we represent our data in some high dimensional space. So that's why we use only 2-dimensional space here to show some
So
data points.
data কি এখানে যে 2-dimensional এটা মিন করছে?
Yes. So basically, we want to show that whatever data set we have, it's coming from some high dimensional space. So number of dimensions depends on number of features. Now here we have only 2 features. That's why we have 2 columns and 2 dimensions. Now, if we have 100 features, that means our data is coming from 100-dimensional space. Now, obviously, we cannot visualize 100-dimensional space because we can only visualize until 3-dimensional space. But the data set we have, it's coming from some high-dimensional space. So that's why we use linear algebra for classification, for regression, for any machine learning task. So if we are not familiar with basic linear algebra techniques, then it will be really hard to understand the algorithms. So we started from data set. So whatever data set, it's basically we can represent that as some numbers coming from some high dimensional space, and then we can convert them to some matrix. If we just have 1 column, then we can convert them to vectors. If we convert them to matrix or vector, that means we can use all the mathematical formulations, mathematical libraries we have for matrix and vectors. So that's the point I wanted to discuss for this slide.
Okay, sir.
Any more questions? So we represent vector as a column of numbers and matrix, basically row and column of numbers. Now, one basic matrix operation is transpose. Transpose means we change the column to row and row to column. For example, if we transpose this is row, this is another row, this is another row, this is another row. So we'll convert them to columns. 1, second column is 6, third column is 3, fourth column is row. So previously 6 was row number 2. Now it is in row number 1, but column number 2, something like that. Similarly, we can even transpose this. So basically we convert the rows to columns and columns to row. That means 1, 2, 0, 4, 3, 9, 1, 6, 8, 7, 0, 2. So here 1, 3, 8 was number 1 column. Here 1, 2, 1, 3, 8 is number 1 row. So that is called transpose basically. Or in notational form, we can write this. Any questions? Now, for matrix or vector, the addition and subtraction is not like normal addition or subtraction. For example, if we have a matrix 1, 2, 3, 4, we can add or subtract this matrix M1 with another matrix having same dimension. Having same dimension means having same number of rows and same number of columns. So we can add it to another matrix -3, 7, 0, 2. So we'll do this operation on those 2 entries. Then for these two entries, however, if we have a different dimension, then this operation is not defined. So we can do matrix addition or subtraction. But for doing that, the number of rows and number of columns must agree for the matrices. And this is also true for subtraction. So that means we do the addition and subtraction on the same elements using the conventional rule of adding and subtracting. But if the dimensions of the matrices do not match, we cannot do these operations on them. Now we'll discuss about dot products of two vectors. So there are two vectors x and y. So what do we mean by their dot product? So dot products is basically we're taking the multiplication of the different components and adding them up. So for example, we have two vectors here. So for this vector, here we can represent y as so we represent at first these two vectors, x and y, and then we multiply the components.
Sir, y minus 4 3 হবে না?
Yes, minus 4 3. So basically feature 1, feature 2. Need to be consistent in representing feature 1, feature 2. So for the data set, again, we'll have something like this. And then there are levels. We do not have levels here. Feature 1, feature 2. So y could be like minus 4 3, x could be three, 4. Now, if we take a dot product, so we multiply minus 4 with 3, minus 12, and 3 with 4, plus 12. So it becomes 0. Now, dot product is 0 if the angle between the vector is a right angle. So if it's 90 degrees, then their dot product is 0. So we can also say that dot product measures the similarity between two vectors. So by vector, we really mean a data point in a space, and then we connect that data point with the origin. Origin means the 0, 0, 0, 0, 0 point. and we call that a vector. So it's basically a line connecting two different points. And we know that only one angle can form between two different points. So we see it here. Any questions?
স্যার এখানে এই ডট প্রোডাক্টের যে জিরো হইলো এটার সঙ্গে স্যার মানে দুইটাকে অ্যাকচুয়ালি 0 0 ইয়ের সঙ্গে মানে এটা করে 90 ডিগ্রি করা আমি ব্যাপারটা ঠিক বুঝিনি।
So,
এটা বুঝছি যে কিভাবে জিরো হয়েছে, বাট এটার মানে রিলেশনশিপটা কি বুঝাইলো এটা বুঝলাম না।
okay, so the relationship is how similar are they? How similar are they really mean how close are they? So we can check with different data points. For example, if we have another two data points, suppose one is here and one is here. So we represent a vector by joining 2 points in figures. The point that we are talking about using the feature values. For example, for this blue point, if it's A and if it's B, for A, for A it is -1 and then 3, and for B it is 1 and 3. Now, if we want to find a dot product,
8 হবে।
so it will be like -1 plus 9, it will be 8. And then we need to normalize it. So basically, the dot product will be between these two points, angle between these 2 points, the value of dot product. So if we want to find the real value, then we also need to find out, we do need to divide it using the length of these two vectors. So the length of the first vector would be √10 times √10. So length of vector A is basically 0 minus 1 square plus 0 minus 3 if we start from 0, and then root of it. Basically 1 plus 9 root, 10 root. Similarly, the length of the vector B will be similar, √10. So it's 8 by 10. It's basically 4 by 5. So now we see that for X and Y, the dot product was 0. We do not need to divide it because it was 0. But for A and B, if we take the dot product, it is very close to 1. And similarly, we can find that A and B are closer than X and Y. Now, suppose we use another example. Suppose this point C. Now we'll take a dot product between B and C. So it should be -2. So C should be -2 and 3. So B dot C should be -2 plus 9
7
equals 7 divided by 10. Now we see that this is 7 divided by 10, and this is B dot C is 7. B dot C equals 7 divided by 10, and A dot B equals 8 divided by 10. So we see that this value is larger than this value. That means A and B are more similar than B and C. So the more close the value is equals to 1, we can say that they are more similar. So by that, what we mean, in high dimensional space, they are closer basically. So it is obvious from this figure, in two-dimensional space, A and B are closer than B and C. And both of them, A and B, or B or C, they are closer than X and Y. So for X and Y, that's why we get a 0 value for dot product. But for other two pairs, we are getting values greater than 0. And always they'll be less than 1 because we are dividing by the length. So they'll be always in the range of 0, 1 to 1. They are more close to 1. That means they are more similar. Was that your question?
Yes, sir.
If
Thank
it's
you.
not clear, you can ask again.
Yes, sir. I actually now understand something. Yes,
Okay.
that makes sense.
So here is the real formula. So we can find the cos theta, or basically theta between them, using this formula. So dot product means they are the corresponding feature values are multiplied and added together. So for here we are representing x as x1, x2 dot xd. It's a d-dimensional vector. Similarly, or we can say it a data point. Y is another d-dimensional data point, y1, y2 dot yd. So their dot product, the first two feature values will be multiplied, added with the second two feature values, and similarly, finally the dth feature values. This is the dot product, and the cos theta between them is this. Now we have a problem here. So if x and y are unit vectors, what is the cos theta? So if they're unit vectors, then cos theta should be x dot y divided by x. This is called norm. That means the length. Y. So it is a unit. This is also 1 unit. So in this special case, cos theta equals x dot y. Normally we keep our vectors normalized, so we directly get this. So in most cases, we keep this as unit. We call them normalizing. So when we normalize them, then cos theta is directly their dot product. Now, what is x dot x? So if we have a vector x, x1, x2 dot xd, what do we get by x dot x? So if we do it, we'll get x1 squared plus x2 squared plus dot xd squared. Now, if it's not normalized, then we'll use x. Now we know that the length of x is x1 minus 0 squared plus x2 minus 0 squared plus xd minus 0 squared, and then root of it. So basically it is x1 squared plus x2 squared plus xd squared and root of it. So that means this is this. So basically x dot x will be like x1 squared plus x2 squared plus xd squared divided by root of x1 squared xd squared times root of x1 squared xd squared. That means it will be 1, because the vector x is completely aligned with itself. So they are most similar that they can be, because we are taking the same thing twice. So they are most similar. That's why we are getting a value of 1. And when they become like perpendicular to one another, then we can check with different values using a coordinate. You can check as your homework. just take points so that they become perpendicular. You'll see that some of them will be plus, some of them will be minus, and they will cancel one another. And they will give us x dot y equals 0 values. So that's why we use a dot product for similarity, and we use dot product a lot. Now we'll talk about some functional forms. So in one dimension, we represent function, linear function like this, function of x equals 3x plus 2. So the function is linear. We have only power 1 for the x terms. So we'll have all the x terms with power 1 here. If it's quadratic, then we'll have some x, they will have power of 2, or sometimes we can have like this x1, x2. So if we add the power of these two random variables, then we'll have 2. This is quadratic. So we can even have higher order functions. Then we'll have like polynomial functions. Then we'll have x to the power p for higher order functions. So this is for one dimension. Now in higher dimension, we'll have different feature values. So basically in machine learning, we only deal with higher dimensional function. Because in one dimension, that means we have only one feature. We have only one feature. When we have multiple features, that means we're dealing with higher dimension. We are dealing with functions in higher dimension. And even in higher dimension, we can have different functions like linear, quadratic, or polynomial. For example, if it's linear in 3 dimension, all the terms will have power maximum 1 or some constant value. For quadratic functions in higher dimension, some of the parts will be quadratic. For polynomial, some of the parts will be polynomial. Or it can have like x1 to the power p minus 1, x2. So something like that. Now again, dot product. So we talked about functions. Now we can see that, now we'll discuss that we can use these linear functions and dot products for designing a classifier. For example, in this graph, we see a line that separates our 2-dimensional space into 2 different regions. Suppose we call this region A, we call this region B. Now we also have the equation of this line. For the red line, this is the equation. Now suppose we are taking 4 different points. This is point A, this is point B, this is region 1, this is region 2, this is point A, B, and this is point C, this is point D. Now, we know that the equation for this red line is this one. So you can rearrange it for x1 plus 3x2 minus 12 equals 0. So this is x1, this is x2. So these are feature values. And in machine learning, any feature values, they are just random variables. So they are capturing one randomness in our data set, describing in that column. So this is one random variable, this is another random variable, and this is the equation for this line. Now, if we put the values of our data points like A, B, C, D, what are they? They are data points in our data set. Now, if we put the values, the feature values for these data points into this equation, what do we get? For A, for this part, the value is 1, 2. Now, if we put here, we get 4 times 1 plus 3 times 2, 7 minus 12, equals -5. For point B, it is 1, 1. So if we put 1 here, 4 plus 2 minus 7, so it was wrong. 7 minus 12 equals 5. And for A, 4 plus 6, so it's 10. 10 minus 12 minus 2. Now for C, the point is 2.
Sir, B -5 হবে না? B equals to -5.
Oh, minus, yeah, sorry, -5. Now for C, it's 2, 2. So we'll get 8 plus 6, 14 minus 12 equals 2. For D, the data point is 2, 4. So we'll get 8 plus 12, 20 minus 12 equals 8. Now, if we check, there is a minus here, there is a minus here. We can say there is a plus here, there is a plus here. So for this region or R1, we'll see that if we put the numbers of our data point or the row in the equation, we'll always get minus values. And for any point in region 2, if we put the feature values for this data point in the equation, we'll always get a plus value. In other words, we can classify our data points using just this line. So that's how we build classifiers. That's what we'll do in especially support vector machine, even in neural network. So if we can represent our data set in higher dimensional space, and we can find different boundaries so that we can easily define classes based on the boundary, we can build classifier based on that.
Sir,
Yes.
can you kindly repeat the part of the positive, negative?
Okay, so I'll include one more point, 2 more points. For example, we take a point here, so it's very close to the boundary. We call it, suppose, E, and we take another point here, F. Now we know we are taking these as our boundary, the red line. Now we'll put the values of E into this equation. So the feature values of E are 2 and 1. Now, if we put 2 and 1 in this equation, so 2 times x, 4 times 2, 8, plus 3, 11, minus 12, we'll get minus 1. Now for F, the feature values are 1, 3. Now if we put in this equation, 4 times 1 plus 3 times 3. So that means 9 plus 4, 13, minus 12 equals 1 or plus 1. Again, if we check, for any points in this R1 region, we're always getting a negative value. And for any points in this R2 region, we're always getting a positive value. That means if we get a new data point in this data set, and we use this equation to get a sign, based on the sign, we can classify the data point. It will be either from positive plus or negative plus. So this straight line is acting as boundary between two different classes. Is it clear? So in machine learning, we have two
Yes,
different
sir.
approaches for classification. One is using probability, that is called generative model. And another one is basically using higher dimensional space. So we discussed a little bit about using probability to find different classes. And now we are discussing using higher dimensional space to find different classes. So I hope it makes sense. Now we'll discuss. So we can use this straight line as a separation boundary. So sometimes we'll use parabola. Sometimes we can use circle. So we can use any geometric shape to find boundary of classes. Sometimes we'll use polynomial curve. For example, we can have separation boundary like this. We can have separation boundary like this, or like this, or even maybe something like this. So we'll see how we can find those separation boundaries. But the point is, we can use any geometric shape to find different regions in our data set for different classes. Sometimes we will use support vector machine. Sometimes we will use logistic regression. Sometimes we will use another trick. But we will always try to find out different separation boundaries. So that's the task of machine learning, finding separation boundary between classes. So that's all. So the linear separators, they take a special form like this. And sometimes we can write them as dot product. So that's why I told you we will use dot product a lot. So basically we'll have weight values or vectors like this, weight, W1, W2, and WD. And we'll have the values of the rows from our data set, X, X1, XD. So these weight values, they will operate on different feature values. So here, 4, 3, they are weight values. So based on these weight values, we can form many different straight lines. So if 4, 3 changes to 3, 4, maybe we'll have a straight line like this. If we have like 1, 4, then maybe we'll have like this. Then these points will be classified for region 2. So we can change the location and shape of the line based on the weight values. So that's why the general form for this type of separation boundaries are captured using this equation. W dot X equals B, sometimes we call B, bias. So bias means the cut. Here we used C or 12. 12 means we don't want the line to go through only the origin point. We want it to cut some y-axis. That means basically we want to draw any line we want, any line we want. That's why we use a C value. If we have 0 instead of C, then all the lines must go through the origin point. To add this flexibility, we add C. So the general form for any separation boundary will be W dot X plus B equals 0. And surprisingly, we'll see that using this linear boundary equation, later we'll find out boundaries like this, boundaries like this, boundaries like this, or like this, 2 different lines. So we can find any form of boundaries using just these linear equations. Sometimes we'll add nonlinearity into it using different functional tricks. For example, when we'll see that when we'll discuss support vector machine, we'll see that we'll change maybe W, maybe X, but end of the day, everything will remain as linear, and we'll be able to find different decision boundaries. So we can even form different. So we need to be able to define different functions. For example, we can define a linear function from R4 to R. That means the function will use 4 features and will give us value of a scalar value. So in 1 dimension. So the function will be something like x1, x2, x3, x4. That means we'll represent it using like this. To get this value, we'll need a vector like for x1, 3, there is no x2, 0. For x3, -2. For x4, 0. So we can represent this function using a notation like this. So we'll use function manipulation to work in linear domain, but find decision boundary in highly nonlinear domain. To define a function defined in 4-dimensional space and the value in 3-dimensional space, we can use a function like this. There are 3 different components here, and so the values are from 3-dimensional space, but we are defining function in 4-dimensional space. That means we are using 4 different features to define the function, but the values of the function, they are defined in 3-dimensional space. So we need to use basically 3 different vectors for that, and then matrix notation. So here x is defined as x1, x2, x3, x4, or square bracket, and then 3 different functional forms should be like this. So for the first dimension, 4 for x1, x2 is -1, there is no x3, there is no x4. Output dimension 1, output dimension 2, x1 is 0, x2 is 0, x3 is 1, x4 is 0. And output dimension 3, x1 is -1, no x2, no x3, x4 is 6. And for all of them, that be dot x, dot x, dot x. In matrix form, we can write this 4, -1, 0, 0, 0, 0, 1, 0, -1, 0, 0, 6. Matrix multiplication, x1, x2, x3, x4. So basically this function we can define in matrix notation like this. So to define matrix vector product, suppose this is matrix. Here we denote that the matrix has number of rows R and number of columns T. So it is R by D dimension. And the vector, it has only 1 dimension D. So basically it's D by 1. Now, the multiplication will only make sense if the inner dimension are same. So it will make sense if these 2 are same. Now we'll multiply all the rows of this matrix and the column of it. So basically if it's M1, M2, dot MR, so number of rows. So the result will be basically R by 1 dimension, M1 X, M2 dot product, so dot product X, M3 dot product X until MR dot product X. That means we are basically trying to find out similarity of this vector with the rows of this matrix. Now, if we know what do we mean by the rows of this matrix, then we'll be able to find out intuition, like why are we really trying to find out the similarity between this vector and the rows of this matrix. So that's the intuition basically. Now there are some special metrics like identity metrics. So in matrix world, if we have a matrix M or A, and if we multiply with I, we get A. So it's multiplicative identity. And here we define it like this. So it the I must have the same dimension as A, and it will have only one in the diagonal entries, and the rest will be 0. Do you need a break?
A break will be great.
Okay, so then we'll take a 10 minutes break. So now, how do we multiply one matrix with another matrix? Suppose you have a matrix A, matrix B has dimension R by K, and B has dimension K by B. Now for them, the matrix must have inner dimension same if you want to multiply them. If the inner dimensions are not same, we cannot multiply them. The multiplication is not defined in that case. So the rule is we multiply row and column. So these are rows, column 1, column 2, column P. The output dimension should be R by K. And each entry Ij this entry will be AI, so this is 1, column 2, column P, Bj dot product. So that means this entry will be the sum of I L A I L B L J. L should be from 1 to K. So each entry, that means the output entry is always a dot product. So that's why I told you the dot product is very important. So it is trying to find all possible combinations of two matrices and the similarity of this row with all other columns. Similarity of this row with all other columns, something like that. So it is a vector, and also column is a vector. So they are trying to find similarity for all the vectors in all possible cases. So in this case, they are trying to find out similarity for all possible pairs. pair with A1, B1, A1, B2 until A1, BP, and similarly for A2 until AR, AR, B1, AR, B2, something like that. It is always trying to find out the similarity. So in short, matrix products, A, B, I, J, it is the dot product of the ith row of A and the jth column of B. And we can write it like this. Now there are some rules. If you use identity matrix, multiply it before or after, it always gives the same matrix. And if we take transpose of the multiplication of two matrices, it is similar to this term. So AB, if we multiply them and take the transpose, it is similar to taking transpose of the second matrix and multiplying with transpose of the first matrix. Now, suppose we have two vectors, U and V. What is U transpose V? So for row and column, that means U1, V1 plus U2, V2, UD, VD. That means U dot V. So if U and V are two vectors in R dimension, and if we take transpose of one vector, matrix multiplication with another vector, basically we find the dot product. Now it's a special case. So we'll need, these terms will come up again and again in the algorithms. So if we understand what they mean, then we'll have better intuition of the algorithms. Otherwise, we'll be forced to implement the algorithms blindly without making any sense, without understanding anything. But if we have good understanding of these simple terms like XTX, XXT, what is dot product, how transpose, how we convert these to this, or this is basically we are trying to find out similarity between two vectors. So if we have these intuitions, then we'll have better intuition of the algorithms. That's why we're discussing this. Now, what do we mean by XTX and XXT? So suppose X equals X1, X2 dot XD. Now XTX should be X1, X2 dot XD times X1, X2 dot XD. So it should be, this has dimension of D by 1. This has dimension of 1 by D. So the inner dimension matches. Now the output should be a D by D matrix, because the output should have these two dimensions. Now the first term should be what? Row, column. So it should be X1 square. Row, column. Row, column. X1, X2 until X1, XT. Similarly, for the second row, should be X1, X2, X2 square, X2, XT. At the end, it should be XT, X1, and finally it should be x d square. So if we take transpose before, it gives us a matrix of d by d dimension. But if we take transpose after, then xt should be x1, x2, dot dot xd, then transpose of x1, x2, dot dot xd. It has dimension of 1 by d. It has dimension of d by 1. So the dimensions just reversed. That means inner dimension matches, the output will be 1 by 1. That means a scalar value. What is the value? x1 times x1 dot x1 plus x2 dot x2 plus xd xd, basically x dot product x. So we know what will happen. So matrix multiplication, they are not commutative. So AB is not equals BA. So you can do the matrix multiplication of these two terms, A, B, and then BA, and you'll find that they're not equal. So I'm not doing it because it's really simple. For the first entry, row, then column. For the second entry, row and then column. For the third entry, row and this row and this column. For the fourth entry, this row and this column, and take the dot product. So similarly, find for this, and you'll see that they are not same, but they're associative. That means we can rearrange the like parentheses. So we all solve the dynamic programming problem of matrix parentheses. So we know that they are associative. So we can either multiply at first these two, then multiply the result, or multiply these two with then multiply with this, then multiply with this. So we can follow any order we want. We'll get the same results. So you can see an example here. Suppose x is a vector, it has length 2. So it has a length 2, that means norm is 2. Now, how can you evaluate this term? So it's xt, x, xt, x, x, dx, x, dx. Now we know that is 2. So we know that this is basically x. You can it has length 2. That means this is square. Because length is this. It means 2 squared, 2 squared, 2 squared, 2 squared. It means 2 times 16 to the power 16. So we can use the parentheses to find out the parts that we know and then combine them together. So now another special case. So for a vector x, we know that xtx is basically the length square. Now, what about this form? And the x has is coming from or x has like d rows, and the dimension of matrix is d by d. So what is this term basically? That we want to understand this term. And surprisingly, we'll find that this understanding this term is really useful. We need it to define and understand Gaussian distribution properly. Otherwise, it will be like one of the cryptic equation possible, the equation for the normal distribution or Gaussian distribution. Sometimes it looks scary, but actually it's a real simple function. So if we understand this term, we'll see that understanding Gaussian distribution is really, really easy. So we want to define what is this? Xt m x. So we can start with a simple x vector. For example, x equals x1, x2. Suppose m equals 1, 2, 3, 4. Just 4 different numbers, d by d. This is 2 by 1 by 2, 2 by 2. We want to find out this term. So xt m x. Now we can at first find out this and then find out this, because we know that matrix multiplications is associative. Now x1, x2 dot 1, 2, 3, 4. So this is 1 by 2, this is 2 by 2. So our result will be 1 by 2. This row, this column, dot product. So x1 plus 3x2. And for the second term, this row and this column. So 2x1 plus 4x2. So x1 plus 3x2, 2x1 plus 4x2. We need to multiply this with x. X is here. X1, x2. So basically, if we think that this is xt, so then x should be this, right? Now, this is 1 by 2. This is 2 by 1. So if we multiply this, inner dimension matches, the output will be 1 by 1. That means output will be a single value, singular value. And how will we get it? Row, column. That means we multiply them together. This row, this column, dot product. Dot product means this one multiplied by this one plus this one multiplied by this one. So if we multiply, we get x1 square plus 3x1 x2 plus the second term. So plus x1 x2 2x1 x2 plus 4x2 square. So finally, the result of these should be x1 square plus 2x1 x2 plus 3x1 x2. That means 5x1 x2 plus 4x2 square. So it is a function from any d-dimensional space to one dimension, and it's giving us a value. Especially, it's not basically any dimension. It's basically it's from any dimension, but it's from d dimension to one dimension, and it's a quadratic function. So basically, this term is defining a function. It's a quadratic function. Quadratic means x will have powers like this: x squared, x1, x2, x3, x4, but no terms will have like x cube or x4. Always quadratic. But the function is mapping any high dimensional space to one dimensional space. So it's a quadratic function. And also there are some important observations are here. So we had a matrix like this. Now, if we check the coefficient of x1, the coefficient of x1 is 1, and this is 1. The coefficient of x squared is 4. This is 4. And the coefficient of x1, x2 is 5. And if we add up, 3 plus 2 equals 5. So that means this matrix is defining the coefficients of the quadratic function defined for vector x. For all the variables in x, all the coefficients for the quadratic terms are in M. So this is a function the matrix M holds all the coefficient for all the quadratic terms of vector x. Clear? I'm giving you something to think. If it's not clear, you can ask questions. Okay, I hope it's clear to you now. I'll go to the next slide. So now we want to find out what is this whole term if we have a M like this. So we already discussed that M holds the coefficient for all the quadratic terms of x. Now if x1 here M is 2 by 2, that means x will have dimension 2. So x will have two different variables, x1, x2. Now, if this is m, then xt mx would be, this is for x1 squared, so x1 squared plus this, and this term will be for x1, x2. So 2 plus 0, that is 2 x1, x2, and this is for x2 square. So coefficient for x2 square. So this term will mean this. So now another special case. So we know that xtmx defines a quadratic function. The terms are like this. Now we want to find out the quadratic function associated with this m. So for this m, we are defining coefficients in 3 by 3 space. That means x has 3 different feature values: x1, x2, x3. Now, what is the functional form? So functional form will be, this is the coefficient for x1 square. So we'll have x1 square plus, this is for x1, x2, not present, x1, x3, not present. This is for x2, x1, it's not defined, and this is for x2 square. So it's a coefficient for x2 square plus, this is coefficient for x2, x3, it's not present. This is coefficient for x3, x1. So 3x3, x1 plus, this is for x3, x2, for x3, x2 plus, this is coefficient for x3 square. So it's always quadratic, always quadratic. So if there are d terms in x, it will have d by d, total d square numbers. D square means for all the pairs of this vector, the values of this vector and all possible pairs they can form is basically d square. And for all those terms, there is a coefficient in m. Any questions? Now it's inverse question. Write the quadratic function f x1, x2 using matrices and vectors. So we want to, so this is our function. We want to represent it using xtmx form. So to represent it, we need to find out x and m, and then we can find out xt and m. Now we have two features here. That means x should be x1, x2. Simple. But what is m? Now, because this is 2 by 2, m will have 4 different values. The first one for x1 square. So this is 1. Then this one will have coefficient for x2 square. This is 3. Now this one will have coefficient for x1, x2, and this one will have coefficient for x2, x1, and order does not matter here. So this x1, x2, the coefficient 2, if we break it into a and b, basically any valid combination of A plus B equals 2 will satisfy. For example, we can have A equals 0, B equals 2, A equals 1, B equals 1, A equals 2, B equals 0, or even A equals -1, B equals 3, A equals -2, B equals 4. So there are infinitely possible combinations of these two variables. So that means we can have values like x1, x2, then maybe 1, 0, 2, 3, and then x1, x2, or x1, x2, then 1, -1, 3, 3, x1, x2, and so on. So I'll stop here for today. If you have any questions, you can ask now. I have 4 more slides. Let's finish it. So there are some special cases for matrix operations. For example, if we have a matrix like, if we take transpose of it and we get the same matrix, for example here, then the matrix is called symmetric. A matrix is called diagonal if only the entries in the main diagonal has values and rest values are zeros, just zeros. A special case is the identity matrix. But normally if all the entries in the diagonal have non-zero values, then we call it a diagonal matrix. Now the determinant of a square matrix. Determinants are defined only for square matrix. So you can find the determinant like this. So it will basically 3 times 2 minus 1 times 1. So you know the rule. We'll take this and the submatrix, then we multiply and get values, and we do it recursively. So for this simple case, 6 minus 1 equals 5. Normally determinant, by determinant we really try to find out the area. So in this example, each row is a vector, our data set. So basically, for example, this is 3, 1. That means 1, 2, 3, 1. And next one is 1, 2, 1, 2. So determinant basically, so we have 2 vectors here. Now, if we extend, if we draw the parallel of this vector and parallel of this vector, we'll get a parallelogram. So determinant will basically tell us the area of this parallelogram. So it is somehow giving us a magnitude or area covered by these 2 vectors. So it depends on the context, how we define it, why we need it, but we have a value for finding the area defined by the vectors we have. So now for higher dimensional case, we'll have some form of area or density, but we'll have some closed form defined by the vectors, and we can measure that. So based on the measurement, maybe we'll be able to find out something, but that's the intuition of determinant. Now, inverse of a square matrix, basically, if we multiply a matrix by its inverse, we'll get the identity matrix. It's like inverse of a number, so that we can, if we multiply, we get 1. Like for 5, if we multiply by 1 by 5, we get 1. So similarly, for a matrix, the inverse is another matrix that if we multiply with the original one, we get identity matrix. Now, we need to be careful that not all square matrices have inverse. So square matrix A is will have inverse if and only if the value is not 0. The determined value is not 0. And we can find square inverse easily for some matrix. For example, for diagonal matrix, if the diagonal matrix is formed like this, D1, D2, Dk, and rest of the values are zeros, then its inverse is easy to find. 1 by D1, 1 by D2, dot dot 1 by Dk. So for some square matrix, is easily we can find the inverse, but there are some rules how we can find inverse of a matrix. It's easy to prove that the matrix is not invertible if we find that the determinant is 0. So this is the last slide for today's lecture. If you have any questions, you can ask.
So symmetric matrix টা তো কি হয়েছিল?
So symmetric matrix means if we take a transpose, we get the same matrix back. So let me go to that slide. Just need some time to save it. So here, if we take a transpose of it, basically if we take a mirror image along the diagonal, we get same values. So mirror image means 2, 2, 3, 3, 5, 5. So we are just discussing symmetric. If we can discuss really optimization, then we'll see that we can use these properties to find out certain operations. For example, for support vector machine, sometimes we can deviate from the dot product and define some other metric. We want to find out if other metric is possible. Then sometimes we need to manipulate this symmetric, if it has inverse, if it is symmetric or something else, to find out the sound condition, something like this. So we are just discussing the nuts and bolts, so that when they come up, we can just use the term symmetric matrix, so that I don't have to explain again what is symmetric matrix, or determinant, what is determinant, or if the determinant is 0, we cannot get an inverse. So if the situation comes up, I don't have to discuss it again and again, because we'll discuss the algorithms, and all the algorithms will use these nuts and bolts to define classification operations or steps. So we discuss the basic things. Was that your question?
জি স্যার, thank you.
Any more questions? Okay, I hope you understood this.